Your applause.
Hi everyone, I'm from Southampton University in the UK, and I'm going to introduce a very small research project that me and four guys who are also in the audience here embarked on our undergrad degree. So one of my favourite creatures is ants. They're capable of incredible collaboration on some amazing projects. They can engineer just like we can. They're also possibly the only animal that has agriculture. There are leaf-cutting ants who farm their own fungus, which in fact only grows in ant colonies, and they use it for food. They're capable of self-assembling into complex structures. There's a species of driver ants who can cross the jungle by day, and then by night they form together and build a structure out of their own bodies. And there are details within that structure. It's not just an amorphous mass. But there's not a single ant there controlling the whole situation. It's just each ant has a simple set of rules that it follows and applies to the stimulus that it receives. And through that, the emergent behavior is really quite complex. The most interesting result of that is that the collaboration scales over millions of creatures in a way that maybe contrasts much of our engineering at the moment. So, wouldn't it be cool if we could do this with robots? That's the drive of swarm robotics research at the moment. These are some research robotics platforms from around the world. The top two from MIT, James McClurkin's Swarm Robotics Lab. Very impressive. And I believe the one on the top left there is the world's biggest robotic swarm at the moment, with over 100 individuals. At the bottom, two from Germany, a very nice collaboration between the universities of Karlsruhe and Stuttgart. I hope my pronunciation doesn't offend you too much. The bottom left one, particularly interesting. It's on the millimeter scale. Unfortunately, that's the only photo I could get, but the top surface there, I think, is 3.5 millimeters long. So really an exciting project. But what really makes these projects interesting is when they scale to large numbers of individuals. And obviously that pretty much comes down to two things. How much do they cost? And can you actually maintain a swarm that large? If you just imagine, I'm sure some of you have got experience with maybe working with microcontrollers or any kind of debugging situation, really. You have to sort of do a lot of tweaks, and there's a sort of cycle of developing and then flashing the code onto the device and plugging things in, unplugging things. Can you imagine doing that 1,000 times over? And what about keeping all of those robots in good charge, and maybe also the mechanics might deteriorate over time? So I think really the answer to maintenance is to get the robots to do it themselves, and we'll talk about that a bit later. So here's our swarm robotics platform. It's the cheapest one in the world, I believe, possibly by a factor of 10. But we think we haven't sacrificed too much functionality. The main thing that makes it cheap is an almost complete lack of custom mechanical components. So everything on there is just a standard printed circuit board, components soldered straight on, including the motors, and that really keeps the costs very low. You can phone up a standard electronics manufacturing company, get of materials and schematics, and they can fabricate these for you for small amounts of money. Incidentally, that's the unit cost for just 25 robots, so a small swarm is affordable just for the maybe the amateur or the very small research group. So at the heart of our swarm robotics system is an MSP430 microcontroller. Many of you may be familiar with these, particularly if you've attended some of the talks or workshops here. It's a 16 megahertz part. It has 16 kilobytes of code space and 512 bytes of RAM. And we think these are sort of a sensible amount of power, which keeps the hardware working and allows some abstraction from that, leaving a little bit of space for some pretty advanced behaviors, which is really the interesting research part for a lot of people. So you can see the robot can interact with the rest of the swarm through its infrared communication channels. There are 3 channels around the device. They're one logical channel, but 3 directions so that you can talk in 360 degrees. And also it can interact with its environment through some sensors and transducers. So it has the motors, which I mentioned, to drive around with. 2 motors in differential drive, so it can steer and so on. Some indicator LEDs to communicate with humans. A photoreflective sensor looking down to measure the reflectivity of the floor. So maybe you could use it to find objectives or maybe even follow lines on the floor. And it has ambient light sensing as well for some rudimentary navigation, which I'll introduce later. So here's the drive system. I'm just going to move through each of these systems and give you a little overview of some of the tips and tricks we've used to keep the simplicity and keep the costs very low. This is the drive system. It uses motors which are typically used to vibrate mobile phones or pagers. They're very, very small and, most importantly, incredibly cheap, particularly because of the large surplus market due to the very quick turnaround times in bringing out new models of mobile phones. Lots of these end up in surplus. So you can pick them up for maybe $1 each. Many of you may have seen a H-bridge circuit comprised of 4 transistors, in this case MOSFETs, to drive a motor. 2 motors, but only 1.5 H-bridges instead of 2. So this saves us 2 components, and more importantly, 2 components worth of PCB space. And the only real functionality we lose as a result is that we can't simultaneously drive both motors in opposite directions. However, we can still turn on the spot by quickly modulating between each motor, drive the left one backwards, the right one forwards, and you'll spin in some direction. And that's fine. We don't even really lose any speed because we're already using pulse width modulation to slow down the motors a lot. We were surprised at how fast they drove when we first turned them on at full power. We were expecting them maybe to lumber along under the weight of the motors, these tiny little motors not really used for driving any mechanical load, but we had a lot of trouble keeping them on the table. We used quite an interesting communication scheme over our infrared LED and photodiode arrangement. It uses a modulation scheme, a frequency shift keying based modulation scheme. Digital data is represented by the frequency of the transmission, like a sort of carrier wave sort of scheme. And the advantage of this is that you can filter with a high-pass filter the communication part that you want to keep and lose the very low-frequency information, which is, not information, noise, essentially, due to ambient lighting. So it makes it somewhat resilient to infrared light, to any visible light from ambient sources. It's pretty much what your TV remote does. We have a rotation-based coding scheme. It's MFSK because there's multiple frequencies involved. There's 3 on the diagram here in the corners. The data is not carried in what frequency you're transmitting. It's carried in the changes between frequencies. So rotating through this coding scheme clockwise will transmit a series of 1s, and anti-clockwise a series of 0s, and so on. You can twiddle left and right to transmit data. The nice thing about this is that it means you don't have to time the interval between two symbols, which is very resource-consuming on a microcontroller. Instead, you only have to notice when it's changed and in which direction, and that's a new bit. It also means that synchronization is very simple. You don't have to maintain a constant awareness of the communications channel. This scheme I've drawn here with 3 dimensions, but it can go up to much larger symbol sets to transmit data faster at the expense of being more error-prone. So at compilation time, you can just give a command line switch and make that trade-off yourself, depending on what situation you may have. So because we use the infrared links primarily for behavioral research. It's very interesting to see how sort of very small local communication interactions, which are very simple and noisy, can sum to a macroscopic behavior over the swarm. This is what most research groups are aiming for in the swarm robotics research. But also it can help us save the maintenance problem. These MSP430s can program their own flash, so with a bootloader we can program the robots over infrared. And when two robots meet, they say, what version are you? Oh, I'm version 2, I'm version 1. Firmware is downloaded across the link, it brings the new robot up to speed. So hopefully you may only need to program 1 or 2, and the whole swarm is suddenly version 3. This itself can be used for some interesting behavioral studies. So there can be a block of code which is integral to the robots, you know, the kind of low-level hardware stuff driving the motors and the communications links. And then the behavioral blocks can occupy a separate portion of flash, and they can be exchanged between the robots. So they can maybe teach a new robot a new behavior by downloading that piece of code across. And so by having a number of these slots which can occupy these, which these blocks can occupy, you can have a community of small subprograms which occupy the swarm, and the total memory of the swarm is greater than the memory of each individual robot, because as long as one robot has the particular code slab for maybe some sort of behavior or maybe a motor test function or something, as long as it doesn't die out in the community, another robot can have a different set of things, and so the total storage is larger. The infrared communications was also a source of genuine emergent fault behavior in our swarm. We had a simple virus-based scenario where the robots would light a red LED most of the time, and then there'd be a sort of green infection that would come into the swarm and propagate, and it would be more virulent than the red and take over the swarm with greenness. But the CRC check in our communication scheme turned out not to be strong enough, and so a whole new orange virus propagated through the community that just took us completely by surprise. So since we have 3 photodiodes for communication, these 3 down the bottom, and are somewhat sensitive to ambient light, we can also use them as sensors. So when we're not communicating, we're measuring the ambient light in 3 directions and use that to get a sort of compass bearing towards the lamp or, you know, the brightest source of light in the room. And to make that robust, we have 2 different bias resistors for each photodiode. One that we use for a high sensitivity mode for ambient light measurement, and then one that's low sensitivity for the communication, which allows high resolution ambient light measurement without the communication being swamped by ambient light. You can also see the high pass filter there to keep those 2 realms separate. We have this floor sensing LED photodiode combination there, and we use that to detect food tokens on the floor. You can also see the battery in the middle there, which is a lithium-ion battery, maybe the sort of size that one would get in a Bluetooth headset or something, but maybe a little shorter and fatter. And it's 320 milliamp hours, which gives us about 1 to 1.5 hours of continual drive time, which also surprised us. That's also as a result of the motors being so much faster than we need. We need only power them for a sort of average 50% of the time or something, and bring the current right down. The robots have these antlers and skis out the front. The skis are to keep them off the ground and keep them sliding around, and the antlers, well, the pair act as a charging input to the robot, so they can drive onto a grounded pad and a powered rail